The solar system is like clockwork. The planets orbit the Sun and changes are quite rare, but occasionally a comet from the cold outer regions visits the inner solar system on an elliptical orbit and sparks some excitement. When getting closer to the Sun, comets form these shiny tails. This phenomenon is caused by the heating of the Sun. The ice changes directly into the gas phase without the intermediate liquid phase. This process is called sublimation and drags the dust along. We call this ejection of dust and ice cometary activity. The sunlight reflected by the dust particles makes the comet visible, but only very few can be observed by the naked eye. The researcher Whipple proposed in 1950 that the source of this ice and dust is a solid core, called a nucleus, like a dirty snowball. Even with telescopes, we can only see the cloud of gas and dust surrounding the nucleus, called a coma, and the tail, but not the nucleus itself. Thus, we send spacecrafts to study the nucleus. This is the comet called Halley, visited by the Jutter mission in the 1980s. One important observation was that most of the sunlight is absorbed by the surface material, described by a very low albedo. Hence, cometary nuclei are the darkest objects in the solar system. Besides Giotto, several other missions were sent to comets, like the Deep Space One, Stardust, Deep Impact and Epoxy missions. Besides many other results, one of the main findings of these missions is that CO2 ice is an important compound that influences cometary activity. With the Rosetta mission, we finally got a more detailed look at the nucleus. After a journey of 10 years, this spacecraft finally arrived in 2014 at the comet called 67P Churyumov-Gerasimenko, in short Chury. The orbiter came really close and even a lander was sent to the surface. Besides many important observations, we are now sure that the nucleus is not a dirty snowball. It contains far more dust than ice, and even if we still don't yet know the exact ratio, we would call it an icy dirt ball. Until today, the mechanisms of cometary activity are still not well understood. One of the major questions in cometary research is, how can comets keep their activity despite being icy dirt balls? We can imagine the cometary surface as a mixture of ice and dust. While approaching the Sun, more and more heat is transported into the surface, forcing the ices to sublimate, even if the temperatures are still very low, like -60 degrees Celsius. We believe that the dust-to-ice ratio of the surface determines whether the sublimation of ices can detach and drag away dust particles. We are simulating this process in the lab with self-made samples composed of ice and dust, and we study the behavior of these materials in a small vacuum chamber. The advantage of lab work is that we can have a look at different aspects separately. For example, we study how the dust is being ejected from our samples. From our experiments, we hope to learn how cometary activity can be sustained over the entire journey of comets through the inner solar system. But this is far from the only open question concerning comets. How can cometary activity be restarted every time the comet comes closer to the Sun? How does the microstructure of the material influence the activity of comets? How can large chunks be ejected? Why do outbursts happen? How does CO2 ice influence cometary activity? All these questions show the complexity of comets. To understand them, we need to put the separated aspects back together. This is no longer possible in small experiments, so we need a large vacuum chamber. In our project, we constructed and built a huge vacuum chamber with an innovative cooling system to be able to perform complex, long-duration experiments while looking at as many aspects as possible simultaneously. This is an ongoing effort, and our CoPhyLab team is motivated to reveal new insights of the physics of comets and their activity. Stay tuned!